Hello guys, welcome back to my channel. So today we're going to do a video on EIGRP. It's a dynamic routing protocol, Cisco proprietary. And so EIGRP is an evolution of EIGRP. Okay, EIGRP, Interior Gateway Routing Protocol. Okay, up to 1993. Okay, then it became enhanced interior routing protocol. Okay, so a little bit of the theory. I'm going to go right to this page here. So as I said, EIGRP was an evolution of EIGRP. Okay, because now it supports variable length subnet masking. Okay, we're going to see a little bit more of that during configuration. It also supports route summarization by default. It supports incremental updates, which means that it's only going to send updates when there are changes in the network. Okay. Other than that, it just sends hello messages. Okay, once every 5 seconds by default. Then EIGRP also supports load balancing. Okay, and the EIGRP multicast address is 224.0.0.10. Okay, so when there are changes in the network, it's going to send a packet to this 2.224.0.0.10, and that all these neighbors are going to be aware of that. Okay, so in EIGRP there are three types of tables. Okay, you have the neighbor table, you have the topology table, and then you have the routing table. Okay, so the neighbor table stores information about all the routers that participate in a neighborship. Okay, and then the topology table is going to store the routing information learned by each router. Then the routing table stores the best routes. Okay. By default, EIGRP comes with administrative distance of 90. Okay, which means it's going to be more preferred than RIP or OSPF, because RIP routing by default comes with an administrative distance of 120, and OSPF 110, 110. Okay, so the lower the distance, the better. Administrative distance, the better. So the EIGRP by default comes with 90 as the administrative distance. Okay. Another thing, EIGRP calculates its metric, okay, based on bandwidth. There are actually 4 parameters. Bandwidth, actually 5. Bandwidth, delay, reliability, load. MTU is not seen here, but you're going to see it in the calculations if we have to do a calculation. But by default, the reliability and the load are set to 0, so the metric is only going to be calculated based on bandwidth and delay. Okay, EIGRP uses autonomous system numbers. Okay, so if a router wants to participate in EIGRP, it has to have the same autonomous system number. Okay, that way those routers are going to form neighborships and they're going to be able to exchange the updates. So one of the advantages of EIGRP is the convergence time, which is actually very short compared to other dynamic routing protocols. So what that means is that EIGRP is going to send updates only if there's a change in the network. Okay, so if there's a change in the network, like if it senses that the route is down, it's going to send a packet to the multicast address, which is 224.0.0.10. Okay, that way all the other routers are going to be aware that there's a change in the network, and they're going to recalculate their routing information base. And then also EIGRP, all routers that are forming neighborships, they have to have the same AS numbers and also the K values. Okay, the K values are the ones that are going to be used in calculating the metric. All right. So the way EIGRP works is that if there's no change in the network, every 5 seconds by default, EIGRP router is going to send out a hello message it's going to send out a hello message to all its neighbors. And then if it doesn't hear back from that neighbor after 15 seconds, which means 3 times the hello message timer, then it's going to consider that route as down. And then it's going to send an update to all the other neighbors. Then they have to recalculate the route internal information base. Another concept that is very much used in EIGRP is the concept of feasible distance and reported distance. Okay, so let's say this router R1 wants to get to this PC. Okay, the PC's IP address is 10.0.1.1. Okay, so there's a concept of feasible distance and the reported distance. From the perspective of R2, if R2 was to share this information to R1, it's going to say, I know this where this PC is, and the distance is 28160. And that distance is called the reported distance, okay? Because remember, R2 is reporting to R1. So R2 reports to R1 saying, okay, I know about this PC, and the distance is 2810. But in reality, for R1 to get to that PC, now it's going to use the reported distance. The feasible distance. Okay, so the feasible distance is going to be the distance that is reported by R2 plus the distance between R2 and R1. Okay, so in total, the real feasible distance to get to the PC is going to be 30720. So it's the addition of the reported distance plus the distance that covers between R1 and R2. There's also a concept of successor route and feasible successor route. Okay, so this is right here. You see in the show EIGRP topology, you see here successors. So there's also this concept of successor route and feasible successor route. So in this diagram that we have right here, we have just R1, R2, okay, and then we have the PC connected to R2. So if R1 wanted to know about this PC and there's another route, okay, other than the route coming from R2, then we're going to be able to see on this routing table a feasible successor route. So as long as this diagram remains the way it is, where we have just R1 connected directly to R2 and then the PC connected to R2, we do not have any alternate route to the PC. Okay, that's why we don't have feasible successor route. Okay, so that's just what I want to mention here. But in the configuration, when we start configuring the EIGRP, we're going to be able to explore that part. We're going to be able to create a situation where we have successor routes and feasible successor routes. We do actually have something here, but that's on the link that I'm going to share on the video description, where you could actually see how the feasible successor routes and the successor routes actually work together. So this diagram here, whereby the traffic goes from R1 to R2 to R4 instead of R1 to R3 to R4. Why? Because the metric going through from R1 to R2 and then to R4, that metric is more preferred. Okay, so this is going to be the successor route, and this is going to be feasible successor route. So this route is going to be used only if the successor route is down. Okay, so that's but we're going to be able to create a situation like this in the configuration. So this is the topology we're going to be using for this for EIGRP routing. It's not too different from the one we use for RIP routing. Okay, so so I have actually altogether about 6-7 routers. Okay, so if we look at the way I name them, I name the connections between routers. So if between router 1 and router 2, so we have 192.168.12.0, okay, /24. So between routers 5 and 1, it's going to be 1.5. Between 2 and 3, it's going to be 2.3. And then I also have loopback interfaces. Okay, those ones for R1 is 172.16. Okay, that's a loopback interface I have for R1, and then R2 is 172.17. R3 is 203.33. Okay. So anyways, that's it for the for this particular video. I just wanted to give a brief introduction into EIGRP routing. So we're going to go into the configuration in the next video. Okay. Thanks so much for watching, and talk to you in the next video.